Greetings to you. We are starting our next session, that is interaction of matter with electromagnetic radiation. Yesterday we had talked a little bit about it, and then we had discussed about the reflection of radiation also. And then I had shown you this slide where the reflection laws are presented. So, earlier I had explained to you that this is the equation governing the reflection. So, when radiation crosses an interface between media differing in different having different refractive index, reflection always occurs. For a beam entering an interface at right angles, the fraction reflected, we normally give it as a ratio, that is reflected ratio, reflected intensity of the reflected radiation, and I0 is the intensity of the incident radiation. The ratio is given by N2 minus N1 whole square divided by N2 plus N1 whole square, where N1 and N2 are the refractive indexes of the two media. So, this is the figure I had shown you yesterday also. You can imagine that the light ray is coming at a slanted angle, which is not exactly perpendicular to the media. I have shown you a media as a glass here, and it comes from the air, passes through the glass and exits at the other end. But you can see that it bends a little bit depending upon the refractive index of the sample. So, whenever we design a spectrophotometer or spectrometer, we have to take care of all these aberrations and then fix the optical diagram, so that the radiation from the source reaches the detector properly. So, that is why we are doing all these kind of exercises. So, that this is refraction phenomena. I have already, this is the refraction phenomena, and the refraction phenomena when it can be defined as when the radiation passes at an angle through the interface between two media having different densities itself, owing to the changes in the velocity of the radiation in the two media, an abrupt change in its direction occurs. So, this is called refraction. So, the extent of refraction is given by Snell's law, that is sin theta 1 by sin theta 2 is equal to N2 by N1, that is also reflected in the velocities of the two beams radiation in the two media. So, we have here sin theta 1 bar sin theta 2 is equal to N2 by N1, that is also equal to V2 by V1, where theta 1 and theta 2 are the angles of incidence and refraction, N1 and N2 are the refractive indices, V1 and V2 are the velocities of the light in the first and second media respectively. Okay. Now, refractive indices of different materials would be different, because they are by nature every material is different. So, refractive index of air is different, and some other gases are different, glass is different, quartz is different, water is different. Like that, there are several materials which are having different refractive indices, but normally the measurement is done with air as one medium and the other as the test medium. So, the refractive indices of different materials as compared with the air are available in the databases. So, whenever we want to design a prism or something like that, we have to see what are the refractive indices of the media, whether it is glass or quartz or something like that. So, in vacuum velocity is change in velocity, that is velocity is 0 and N1 is unity. So, we can write instead of N1 by N2, we can write N2 vacuum is equal to sin theta 1 vacuum divided by sin theta 2. So, such calculations are possible whenever we want to design optical table for the infrared radiation to pass through the different parts of the instrument. Then we should know a little bit about scattering of radiation. So, here momentary absorption of radiant energy by the atoms, ions and molecules, normally they are followed by re-emission of the radiation in all directions. That is known as scattering. Suppose I have a small particle, radiation comes, it will scatter the radiation. It is a very well known phenomena and experienced by all. For example, in the room where you are sitting, if there is a light source, it just does not travel in straight line and leave the remaining parts dark, is it not? So, the remaining parts are also illuminated because the incident radiation falls on the particulates, air, etc., and then gets reflected in different directions, not necessarily in the direction of propagation. So, that is known as scattering. And what makes the scattering phenomena universal? Because it is observed whenever there are atoms, whenever there are ions and whenever there are molecules, and these things are always there in the air, and then plus there will be particulates in the air. So, all these things when they fall on the particles, re-emission of the radiation occurs in all directions, and particles having comparable dimension to that of the incident radiation. See, here we are assuming that the wavelength, that the electromagnetic radiation is like a particle, corpuscular theory, and like a photon, the size of the photon having a comparable dimension to the particles present in the media, then it removes most of the re-emitted radiation by destructive interference, except those travelling in the original direction. So, a very small fraction of the radiation is transmitted at all angles from the original path, and its intensity increases with the particle size. So, what we are talking here is, if the particles are very small, of the size comparable, the scattering will be minimum, that is the bottom line. So, scattering by molecules or aggregates having still smaller dimensions than the incident radiation is called as Rayleigh scattering. There are three different kinds: particulates having equal, almost same size, and particulates having smaller size than the electromagnetic radiation, that is the amplitude. We are talking about the amplitude of electromagnetic radiation. The amplitude is measured in distance. So, the particle size also can be measured in distance. So, we are talking about the interaction of equivalent size particles, smaller particles and bigger particles. So, scattering by molecules or aggregates having smaller dimension is called as Rayleigh scattering. Okay. Then larger molecules scatter radiations in different quantities again, but that too in different directions. This is called as Mie scattering, MIE, Mie scattering. And when the scattered radiation is also quantized to some extent, like those occurring in the vibrational energy level or rotational energy levels, etc., the transitions in the molecules as a consequence of polarization process, it is called as Raman scattering. So, this is the Raman scattering in terms of quantization, which won the Nobel Prize for Professor Raman in 1931. So, Raman scattering is also very typical of several materials, and we need to know. Nowadays, there is a separate branch of science for the identification, differentiation of particles and chemicals, etc., by Raman spectra also. So, that we are not going to study Raman spectra right now, or not in this course anyway, and but it is good to know that the radiation scattering is a phenomenon occurring everywhere. It occurs inside the instrument, and this scattering is of no use in general, because the scattered light does not reach the detector 100%. So, in an instrument we want the scattering to be minimum. So, the optical path should be very precise, and there should not be many particles in between the source and the detector, that is air particles and things like that. Plus we also want the if they are there, it should be minimum. Usually most of the instruments do have about 1 to 5% of scattering, whatever you do, however dark system you make, still there will be you cannot make an instrument without joints. So, there will be some parts to be joined together, etc. If you observe any machine, you will see that it is composed of several components, and which are joined together by either screws or press fit or something like that. So, they cannot altogether stop the scattering of the radiation, and instruments are no exception to this rule. So, it is not possible humanly to eliminate scattering totally, but it is possible to minimize. We can paint the inside of a spectrophotometer black, so that it absorbs all other radiation, etc. But the best one can achieve is approximately about 1% of scattering. Less than that, it makes the instrument very costly and may not be worth it, but more than that means there is some problem with respect to the sensitivity, that is the minimum quantity that can be detected or determined in presence of high scattering, this thing, that is a little bit of a problem anyway. So, now having known so much about the scattering, we are going to talk about polarization of radiation. So, polarization, I think many of us know, we have seen the effect of polarization in our day to day life. Whenever you see two pictures imposed on one another, especially in TVs and movie halls, if you are looking at the screen, you will see that one picture is imposed on another quite often. So, that is all effect of polarization. So, ordinary radiation usually consists of electromagnetic waves, in which vibrations are equally distributed among a huge number of planes centered along the path of the beam. Here what I am trying to tell you is explain to you the phenomenon of polarization. So, what I am trying to tell you is ordinary radiation. It consists of bundle of electromagnetic waves in which vibrations are there in all sides of the propagation. Okay. So, there are a huge number of planes centered along the path of the beam in general. So, one is electromagnetic wave, another is a electric field, one is magnetic field, like that. Even those fields, there will be slight variations, and there will be a bundle of electromagnetic field around the propagation path of the radiation. That is what I am trying to tell you. So, viewed end on, how does it look like then? It looks like an infinite set of electric vectors fluctuating from 0 to a maximum amplitude, that is we can denote it by A, and this is how it looks. Okay. So, here I have an incident beam unpolarized on the left side. So, you can see here there are number of planes, amplitudes, but all those amplitudes are not only perpendicular to the plane of propagation, but they are also oriented in different planes. So, this is what we normally see in unpolarized light. So, polarization of so we said there are number of planes that are present along electric field and magnetic field oriented in different directions in the space along the propagation field. Okay. So, the vector in any one plane, say x y, it can be resolved into two mutually perpendicular components. We have already seen that. So, removal of one of the resolved planes of vibration produces a plane polarized beam. That means, in general there are sort of when the propagation is going on like this, I have the amplitude electric field as well as magnetic field. Suppose I remove the electric field, then what I have here is what comes out. I put a barrier to stop the electric field to come from coming, and then only the magnetic field will be there oriented parallel to the propagation of the incident beam. Similarly, if I remove the magnetic field, there will be only vertical propagation. So, that means the radiation that comes out after the interference will be more disciplined, we can say. So, polarized they all occupy by a single plane, and radio waves emanating from an antenna and microwaves produced by a klystron tube are usually plane polarized. If you wish to know more about it, you can take a look at how the antenna, radio waves and other things are emanating from a radio station, etc. The information is available in the YouTube or Google or whatever it is. So, polarized ultraviolet and visible radiation is normally produced by passing EM beam through a media that selectively absorbs, reflects or refracts refraction that vibrates in only one plane. So, that is the how we understand. So, here I do this, I have a barrier here to stop all these haphazard planes, and then a vertical barrier I have introduced. So, I am getting only one beam horizontal. So, this is vertically polarized light beam, depends upon your perception, okay, vertically or horizontally, how you look at it. And then now I want to talk to you about dispersion, but dispersion is a little bit of a complex phenomena. Dispersion curves usually show two regions. One is normal dispersion, in which there is gradual increase. I have discussed this earlier also a little bit. Okay. So, anomalous dispersion occurs coinciding with natural harmonic frequency of some part of a molecule. That means, the dispersion curve will not be changing uniformly, there will be abrupt changes. That is what anomalous dispersion occurs. So, in spectroscopy we want dispersion curves to be sort of ordered and disciplined. We want uniform change in the dispersion instead of abrupt changes. So, dispersion curves are important for optical components such as lenses or even mirrors, and then most suitable components for the manufacture of lenses are those in which refractive index should be very high and constant also throughout the media. So, this results in reduced chromatic aberrations. So, the fabrication of prisms, refractive index should be as large as possible, but it is also normally our experience is it is frequency dependent. So, this is a figure of dispersion for quartz, and you can see that here I have plotted 10 frequency here 10 raised to 13, 14 and 15. This is the refractive index, but what is coming out is this is all normal dispersion, but anomalous dispersion is here. See, it keeps on gradually increasing, okay, and then it keeps on gradually decreasing. Here the slope is different, okay. Here the slope is different. These things should not be there as far as possible, okay. So, this is known as anomalous dispersion. because if the material is of uniform dispersion, it should be just like this, or it should keep on increasing depending on the thickness. So, another phenomena that you should know about the interaction is diffraction, interaction of EM radiation with matter. So, diffraction refers to the bending of the parallel beam of electromagnetic radiation as it passes through a sharp barrier or a narrow opening. It is a consequence of interference which can be demonstrated in the laboratory. It can be destructive, it can be constructive interference also. So, what is important is when a parallel beam of radiation like this falls and allowed to pass through a small pinhole, two closely spaced pinholes I make it on the screen, allow them to pass through. So, then on the screen, suppose I place a screen on the back side of the pinhole, what do I see? I see dark and bright stripes. So, if the radiation is monochromatic, that is having a single wavelength, all the radiation should have a single wavelength, that is known as monochromatic radiation. So, monochromatic radiation, if I use, a series of dark and light images appear perpendicular to the plane of radiation. I will show you the figure here like this. This is a pinhole here, this is a screen, radiation is coming out like this, and then I have, this is the media. The white lines you see on the left side of this figure is the media, and the radiation comes out like this. But what you see on the screen after this pinhole is, you will see bright patch, small dark patch, bright patch, small, like this. They are all differing in intensity. This is known as pinhole diffraction. Okay. Now, if I have two pinholes like this, here I have seen O, B, O, C, two pinholes I have seen, one is B, another is C, O is the midpoint. What I see here is a number of crisscrossed interaction of the wave beams, okay. And here I have on the left side the parallel beam, this is the parallel beam, and diffraction by single slit will be like this, dark patch, white patch, dark patch, white patch. But if I do it with the two pinholes, I get to see a series of interactions, and if I catch it on the photographic plate, I see, you can see I have shown it here, that is X, DE, and then Y, this patch. This is something like a photographic plate. You can see dark patch, white patch, dark patch, white patch, like that. It will, there will be a series of dark and white patches you will be seeing. This is the phenomenon of diffraction. Okay. Now, we can show that this phenomenon of diffraction, there will be the distance between the bright and dark patches can be calculated depending upon the incident radiation as well as the distance between the two pinholes. Okay. So, I will not go into details of this, but you can see these things in Eyring Walter Kimball, where or Willard Merritt and Dean also, Skoog also, you will see this phenomenon explained very nicely. Okay. Now, I can show you that in the previous figure, the distance between the two fringes can be, I can show that CF is equal to BC into sin theta. For two beams to be in phase, we need to have this, and reinforcement occurs at 2 lambda, 3 lambda, etc. Hence, n lambda is equal to BC into sin theta, where n is an integer called the order of interference. So, I can expect number of interference fringes. So, n is equal to 0, n is equal to 1, 2, 3, 4, etc. So, depending upon the number of pinholes and other things I get different constructive and disruptive patterns. So, when the phase differences remain entirely constant with time, the system is said to be coherent. You should remember this. So, then only a regular diffraction pattern can be obtained. So, what about the spacing then? The spacing of the bands depends upon the distance between the slits, that is denoted by d, and this following relation holds to determine the spacing between the two bands, that is n lambda is equal to d sin theta. N is the order and lambda is the wavelength, d is the distance between the two spacings, and theta is the angle of incidence. Okay. So, if two different wavelengths I use was, for example, one red light and one blue light, the two colors will be separated on the screen. That is the beauty. You can see both blue and red patches on the screen. So, but if I use a white light, a number of small rainbows are containing all the colors will appear. So, by placing a moving slit across the screen, I can have any color or wavelength selected. This is the principle used in gratings, because in any spectroscopic technique, what I need is an electromagnetic radiation of a specific wavelength. So, this specific wavelength, how do I select? For example, I have a source means a lamp, it gives all kinds of wavelengths corresponding to infrared radiation or spectroscopic radiation. But I need to, when I want to scan, I need to have only one wavelength, stopping all other wavelengths reaching the sample. So, how do I select from a given source the correct wavelength which needs to be passed through the sample? That is done by gratings. Okay. So, what I do is I have already shown you the picture, that is this one. So, here I have shown you that you can get different colors. So, if I put my detector here, it will detect only the radiation coming in this range. If I put a detector here, for example, it will show the radiation coming through this. That means, I can choose different wavelengths from a diffraction grating to cover the entire range of the electromagnetic spectrum corresponding to infrared spectroscopy or this thing. So, essentially it works like this only. For example, here I have shown you a prism, and here white light comes, and then all other colors get separated because of the refractive index. I put a screen here, and if I put a hole here, I will get red. If I put it here, I will get orange. If I do it here, I will get yellow. I put a hole here, I will get blue color. Like that, I can choose any color that comes out of the prism. Exactly same thing happens when I am using grating, but in grating what happens is the wavelengths are more precise than the prisms. So, we will see about gratings, how they are made, etc., in some other context later, but essentially gratings and prisms do the same job. Okay. They separate the different wavelengths of the incident radiation, and by placing a prism I separate, and then I put a mechanical hole in front of the separated radiation and pick up the exact wavelength whatever I need. or I can make the slit move from one end to the other end and then scan the whole lot. So, I have a choice of using a prism or a grating in a given instrument. Okay. So, then how does the prism work? Prism also works on the same principle. I have a prism here in this slide, you can see this. It disperses the incident radiation depending on its refractive index and its variation with wavelength. Okay. So, that is the principle function of the prism. So, a prism can be used to disperse. I can disperse ultraviolet rays, I can disperse visible rays, I can disperse infrared and several other things also. So, to disperse these things I can use a prism or grating. Okay. Now, the material of construction, which material I should take, glass prism, quartz prism or polystyrene prism. You know, there are many prism materials which have different characteristics. So, the material of construction depends upon the wavelength region which we want to select. So, here I am showing you two types of arrangement. One is a prism with this is a 60-degree angle, let us say. This is a sort of isosceles triangle. So, this is 60, this is 60, this is 60, okay, all the three angles, and a prism is made like this, and inside white radiation comes here, then it separates into different materials. The extent of separation depends upon the material as well as its refractive index, and I get the things like this. Here it is 60 degrees. Now, what I am going to do is another way, that is I cut this into two parts, this prism. So, here I have cut and taken only one part, but I am going to put a mirror here. Okay. That is what I have shown on the right side. So, this is known as 30 degrees prism, because if I cut this angle into 2, I get 30 degrees, and now I have a half prism in my hand. In this half prism, the one part is rectangular, remaining part is remain just like what it was earlier in this arrangement, but I have mirrored it here. So, what happens? Any radiation that comes in goes here, hits the mirror surface, it cannot pass through, it is reflected back and comes out on the same side. So, you can see the difference between these two, that is if I use an ordinary prism with 60-degree apex angle, I can get the same separation, okay, on the other side of the light that comes that is coming in. It comes in at this angle, but on this side, but my radiation collection should be on the other side. Here if I use only 30-degree prism with 30 degrees apex angle and mirror it on the other side, the radiation will come here, go here, traverse the same path. That means, the distance travelled will be exactly same as this if I mirror the one side. So, this is there are two different types of arrangements. One is I can take two 30-degree prisms. If I take one more and fuse it here, I fuse it here, I get 60-degree apex angle. So, a prism can be constructed by fusing together two 30-degree prisms. This is called as Cornu type. So, try to remember, this is Cornu, 60-degree prism is Cornu type and 30-degree prism is Littrow type. Another arrangement is to use 30 degrees with prism mirrored black, this is called as Littrow type. In Cornu mounting, the dispersed radiation is collected across the prism, and in Littrow mounting it is collected on the same side. Okay. So, The only difference between the two, Cornu mounting and the litro mounting. So, in actual instrument, in litro mounting, refraction takes place twice on the same side with less material coupled with the saving of space. So, in most of the analytical equipments or infrared spectrometers, what I have is, if you want to make the instrument smaller, we would like it to be sort of litro mounting. But if the instrument earlier in Russian models etc., instruments used to be huge, because they will use bigger prisms and things like that, and every instrument used to be taller and bigger than a human size. But nowadays, thanks to technology, all these things have become tabletop, bench top, portable. That is the beauty of the instrument. So, this is another way of looking at the apical angle, and this is the litro mounting. You can see that the radiation comes in and hits here and comes back, and it gives you different red, blue, like that, different radiations. So, this is a grating. Here you can see that the prism, there are, you can see here in this area figure there, it looks like a boat now, but earlier it is essentially a collection of small prisms. You can see in the figure, you can see small ridge like thing, okay, like this. There is one here, one here, one here, 1, 2, 3, 4, 5, 5 ridges are there. That means I have made 5 prisms here with the same in the same size. So, this is the cross section of a diffraction grating showing the angles of a single groove, which are microscopic on an actual grating. Okay. We will continue our discussion in the next class.